All right, thank you. Thank you for the introduction. Happy to be here today to present about our work on the robotic knee prosthesis with torque-sensitive elastic actuation. Let me talk to you a little bit about the state of the art in knee prosthesis. There are two main kinds, passive and powered. Passive prostheses are very much dampers. They provide some support and stability, but they cannot inject energy like our muscles do, making ambulation very difficult for amputees. Power devices aim to solve this limitation with actuation and batteries. However, they're also much heavier than their passive counterpart, and this added weight significantly challenge amputee gait, stability, and effort, and limit their clinical success. But why are power devices heavy in the first place? One of the main reasons is that most of them have electric motors coupled to a fixed gear transmission, and motors are preferred because of their high efficiency, but they are only efficient within a very small operating region, in particular high speed and low torque. However, the knee, as you can see below, contains both high torque, low speed, and low torque, high speed requirements for activities in daily life. And thus, designers have had to compensate with big motors, batteries, and transmission. The design of a prosthesis that is both powered and lightweight remains an open challenge, a challenge that we propose to solve with a torque-sensitive elastic actuator. The actuator is essentially a linkage system with 2 degrees of freedom coupled to an electric motor. As you can see here in the mechanism, it has 2 degrees of freedom. One is the rotation of the knee joint. And the second degree of freedom, which is a conceptual innovation here, is a translation of the torque-sensitive joint B along a straight slot. And the joint B is also connected to a spring AB and also to the bolt screw C, which is driven by a motor connected to a rigid bar BC. And the torque created by the motor to extend the knee will also extend spring AB, effectively enlarging the leverage OB and increasing the torque ratio. And pretty much the system acts as like a variable transmission system, and the motor can still remain in its optimal torque speed operation, even though the torque requirements of the knee vary to match the needs of ambulation. One thing to note, though, is that this mechanism, due to the geometry, adapts non-linearly to knee extension torque and knee angle, and is not intuitive to design a dimension to get the most out of the actuator. We then also developed a holistic design framework that obtains the required knee torque, speed, and power from normative biomechanics, and that we use them as input for our dynamic simulation programs in MATLAB. That contains also the complete analytical model of the mechanism, and it can be used to obtain the optimal design solution that minimizes the combined weight of the power screw, the motor, and the battery. And then we use that optimal design solution and design the structural frame in SolidWorks. And we use FEA to guide our process as well, to make sure that the structural frame can effectively dissipate the heat generated from the motor, as well as sustain the torque and speed, torque and load requirements from ISO standards. The overarching goal is to design the lightest knee possible while still satisfying usability and performance. And I'd say we achieved that goal. Now let's see the leg in action. Here we have the powered knee and also our custom ankle foot prosthesis being worn by an amputee, and he's doing walking and stair ambulation very smoothly. You can see the variable transmission acting, supporting both high torque and his whole body weight, and also high speed to timely swing the leg forward. The real show of performance here is climbing stair 2 steps at a time, very demanding in both torque and speed. In conclusion, we have designed, developed, and tested the lightest powered knee available both among commercial and research devices, and even matching the weight of a passive microprocessor device. And we achieved that with a nonlinear torque-sensitive elastic actuator combined with a holistic design framework to achieve high performance and minimal device weight. Thank you.